Okay, so happy to make this as informal as we'd like and stop and ask questions along the way. I'm going to drill down into some of the results that we've had from this integrated cropping systems trial project, and try and get at this question of, can we sequester carbon in agricultural soils? And the answer is yes. We just have to get a long tube and blow a lot of CO2 down into the soil and keep it. This is Greg Sanford again. I don't know what he's doing here, but he's, I think, trying to install some lysimeters into the soil. But I just thought it looked like somebody trying to sequester carbon in soil, no matter what. So Greg's had a big hand in the work that I'm going to talk about. And then again, I want to point out Anna Cates, who has done quite a bit of work looking at carbon balance in cover cropping systems. So why might we want to store carbon? I like this cartoon. I use it in class a lot. It's trying to get at what we're actually trying to do when we talk about stabilizing climate, which is we're trying to undercut this number here, which is 4 petagrams of carbon per year in the atmosphere. That really is the balance of the 9 that we're putting into the atmosphere as a result of fossil fuel combustion, and the extra 2 and the extra 3 that we're getting through photosynthesis and carbon uptake from the oceans. And so that balance between the 9 out and 5 in is this 4. And so there's a lot of, I would say, I think one of my main takeaway points today is going to be an overly optimistic notion that somehow we can increase either the photosynthetic capacity to do this, or somehow suppress the respiration, the loss of carbon from the atmosphere, from the soil to the atmosphere. But nonetheless, these are sort of the big arm-wavy, big-scale numbers that we are trying to get at. And recently there was this paper that came out in Global Change Biology talking about land use and, what kinds of numbers may or may not be reasonable, but nonetheless would be needed in order for us to get close to the 4 petagrams of carbon per year. And so here they indicated that there's some ability, they think, of increasing carbon sequestration as a result of forestry, of increasing it as a result of crops, and increasing it in grasslands as a result of grazing, to the tune of, I don't know, if you sum that all up, maybe it's 5 or 6 petagrams per year. So the notion here is that we could improve management of forest crops and grasslands to help meet that goal of undercutting that 4 petagrams a year. At the same time, of course, we're going in the wrong direction with respect to positive feedbacks to the permafrost, where the increasing temperature is actually causing more and more carbon that's locked up in permafrost to go into the atmosphere. So these are sort of the big arm-wavy numbers that we're talking about. And again, just for context and scale here, I did some back of the envelope calculations. This map is just sort of for context to look at total MPP each year. So this is net primary production. This is all of the carbon that's fixed by plants and stays in the plant at the end of the year. So it's above ground, it's below ground, everything sort of mapped across the Corn Belt. And I know you can't read these from back there, so I'll interpret here. The red numbers are in the range of 13 megagrams per hectare per year of carbon. So anyway, the big picture here is that we're really talking about gains of about 5% of net primary production. So if we're going to do something to improve forestry or improve crop management, we're talking about improving yields, basically, by about 5%. So I think these numbers give some context that we're not talking about, some crazy big numbers, but we're also talking about significant change when it comes time to increase carbon that's going to help stabilize climate. So that's sort of on the input-output production side. The other thing that gives us some hope that we might be able to store carbon that might help stabilize climate is this cartoon, which I apologize, it's so grainy. But this is time since cultivation here on the x-axis. You might recognize this. It's from sort of the Bible of soil science, which is from Brady and Weil. And so this is the passive organic matter fraction of soil carbon This is the slow organic matter fraction. This is the active organic matter fraction. And then this last fraction is just plant residues that have built up in the soil. So this is the way we tend to think about the soil carbon pools. And these, this passive fraction is really what we think about when we think about sequestering carbon. And this, I think, is a big sort of misunderstanding when it comes to how we build up carbon in the soil. Just building organic matter and piling up organic matter at the soil surface really is sort of increasing these plant residues a bit. But then there's all this transformation of that carbon that happens through time that ends up in this carbon, the passive organic matter, where it's really, we really consider it sort of sequestered and taken out of the atmosphere and not likely to get back into the atmosphere very soon. And so this is why I think a lot of times I go to talks and hear anecdotes about, I started doing this land management 2 years ago and I've increased my organic matter from 3% to 12%. And I'm always thinking, that's all great because building organic matter is a good thing. I'm not saying it's not a good thing. But when we're talking about like trying to store carbon to help stabilize climate, most of that carbon is going to get back into the atmosphere pretty soon. A fraction of it might end up being sequestered. So when we talk about carbon sequestration, I think that's an important, down in the weeds detail. So as I just said, building organic matter in agri-ecosystems is a good thing. It's climate stabilization notwithstanding, because we know that it helps improve crop yields by building the water holding capacity of the soil, by helping hold on to soil and keeping it from eroding. We increase the infiltration capacity of the soil when we do this. So piling up organic matter is a good thing. I just want to make sure nobody goes away from this thinking I said it wasn't, because it has these other positive impacts on our agronomics. There have been lots of practices that have been promoted and touted as being ways of possibly increasing and building up carbon in the soil. And I've listed those here. The first is reducing tillage intensity and frequency. Some of you may know that this is quite a controversial topic. There's a lot of discussion in the literature still about the relative merits of no-till versus even moldboard tillage to build up soil carbon. For a long time we thought moldboard plows, bad thing, you tear up the soil and you break up and oxidize carbon. No-till is the way to go. Of course, over time, as we've looked at depths, we've started to learn that, well, no-till probably helps us build carbon in the upper few centimeters of soil, but the moldboard plow actually buries a lot of that carbon, so doing that occasionally might be a good thing. And I think this is still something, it's still an argument that's being debated in the literature. Applying manure has been discussed as a way of increasing not only productivity of the plants, which should help lead to more carbon input into the system, but as a direct input of carbon into the system itself. Using cover crops, of course, I tried to dismiss this a little bit. I think that it can have positive effects on soil carbon in some places, but I don't think it's just sort of a blanket statement that they help improve the carbon situation. Optimizing fertilizer applications so that we're not putting it on in times when the plants can't use it is something that's been considered. And then getting into my sweet spot here, planting perennials, increasing plant diversity, and improving grazing management. These last three are sort of in the grassland realm, and something that I get really excited about. So we've published some articles here addressing these first three. This is in red because these articles in particular have shown that these things really haven't helped carbon accumulation. Matt Ruark published, he's from the University of Wisconsin-Madison as well, published a paper showing that optimizing fertilizer application doesn't really help increase carbon storage, but maybe it helps hold on to what's there. And then we have several papers that have been put out recently about grasslands and increasing diversity and improving grazing management. And these I've put in gray because the takeaway message from those, as ecologists usually say, is it depends. Sometimes we get carbon storage, sometimes we don't. Sometimes we get it over there and not over there. And so, there's no blanket green or blue papers here where we can say, here's what we need to do to store carbon. Because the takeaway message for this whole talk is that I don't know what the answer is to that other than plant for perennials and work to undermine fossil fuel combustion. That's really the takeaway message I would want to leave you with. And here's why. I mean, if we talk about why carbon might accumulate in the soil organic carbon, the only reason it will accumulate in the soil at some big high level is that NPP, the net primary production of the plants, so that's all the carbon that's fixed by the plants and stays in the plants, it has to be greater than microbial respiration. So this is respiration by heterotrophs. Heterotrophs are the microbes in the soil and other creatures in the soil too that are trying to get at the carbon that's in the soil, that's dead plant residue, to use for their own bodies and then use for their own respiration, to build their own bodies and do their own business. Well, if that outstrips that, then we're going to lose carbon and vice versa. If NPP outstrips microbial respiration, then we at least are setting ourselves up for the potential to store soil carbon. And the main controllers or drivers on that are precipitation and climate. And we are smack dab in the prime country for building carbon because the combination of annual temperatures and annual precipitation set us up perfectly to have a lot of NPP during part of the season, and then as we're about to find out in the coming months, not much activity at all, not much NPP, if none, although sometimes I wonder. And then in the wintertime, of course, that microbial activity slows down. It doesn't stop altogether, but it slows down enough that we tend to hold on to a lot of that carbon that came into the system. So the carbon comes into the system as plant carbon that's fixed, and then it goes out as carbon that's respired by microbes. So anything we can do to increase plant growth and slow down microbial activity is a good thing, but of course there's the rub that the microbial activity is also the thing that makes nutrients available for plants to grow, so there's always this inherent tension. But the takeaway for this is there's a reason this is the Corn Belt, there's a reason these are mollisols, it's because of the combination of temperature and precipitation. But of course our land use has undermined that over time. Secondarily, I would say soil traits are super important for helping us understand how and whether soil carbon can accumulate. And we break those down typically into physical, chemical, and biological realms. And 125 years of agronomy and soil science broke those down into those three, and everybody became an expert in one of those boxes. And nowadays, Anna Cates, my grad student, her job is to tie these back together and say, no, we can't focus on one and ignore the others. It's all about all three of them. That's what we think of soil health as, some intersection among the constituents of these three things. And what's really exciting about this, I think Julie will say, because even though she doesn't just focus on this and ignore these, this is maybe her bailiwick, more and more we think that understanding who's in the soil, which microbes are in the soil, and how they're doing their business is super important to helping us understand how and whether carbon's going to accumulate in the soil. And so I want to share some data later on to get at that a little bit. Historically, we've thought about the carbon that is in the soil in these sort of three categories. I showed you that earlier diagram that showed carbon slowing down. That's one way we think about it. Another way we have thought about it is that there's this unprotected carbon. This is the plant stuff that's just, if you took a handful of soil and looked at it with your naked eye, you can still see pieces of plant material. If you looked under a scope, you would still see plant cells. You identify it as plant material. That really is what we consider this unprotected carbon, this detritus. Most of that is likely to end up in the atmosphere eventually, but some of it we hope will get protected either biochemically, meaning that microbes can't really get at it very well with their enzymes and exudates, or physically, meaning that it's gotten occluded by soil aggregates. And this is one of the reasons that soil aggregation is a really important thing when we're looking at soil carbon. And then, of course, management is a huge controller or driver of whether or not carbon can accumulate in soils. But I think an open question is whether or not management can do anything in the face of a changing climate. And that's sort of part of that thing I teased at the beginning. If we're off on some directional trajectory now where the microbes are being stimulated so much that we're losing more and more carbon, it may be that there's no amount of sort of management or what we think of as typical management that we can do to help slow down the loss of carbon from the soil. So, apologies for the academic overview here, but are there questions or comments that people have before I start getting into some data?
Just one comment. You mentioned something about lower pounds you brought up every couple of years. I disagree with that wholeheartedly, because aren't you putting air or oxygen in the soil and that helps burn out carbon?
Yes, that absolutely is happening when you oxidize. You know, you're making carbon available for oxidation by pulling up carbon from the depths. I think part of the argument, though, is that once you've done that, once you've sort of exposed the carbon that's there, continuing to mix it might be a better thing because you get some of it down there and not sequestered, that's not the term I want to use, but packed away, farther away from the oxygen sources so that it has a higher chance of being sequestered in the long term. I don't subscribe to that either. I'm just trying to tell you what the argument is.
Doesn't that make it anaerobic? When you're plowing down 8 inches, there's no oxygen getting down there, that's locked up, basically.
Right.
And you bring it back up, and it's going to go up anyway.
Right. And so I think the argument is that on net, the balance of those things is that, you know, over time, some of that will leach down, get below the mold or plow layer, and so we have a better chance of getting it down there sort of below where the plow layer is going to be. Yeah.
I call that recreational tillage.
Recreational tillage. Your point's well taken. I think one of the takeaway messages from all this is going to be that we need to not disturb the soil in order to build soil carbon. Well, and here's part of why. I guess I'm not done with the academic part yet, but this is so cool. Clay, I think you've seen this before from grassland ecology, and I always come back to it. Howard Skinner in Pennsylvania put out these soil carbon monitors, we call them eddy flux covariance towers. But what they do is they basically measure the carbon above the plant canopy continuously, and using some calculus, relate the wind speed and direction to the carbon concentration above the canopy, and estimate in real time what the carbon flux is between the canopy and not just the canopy, but the canopy and the soil and the atmosphere. And so what we see here, this is pretty convoluted, but hang with me here. He did it over grass and he did it over alfalfa. So the dark is grass and the open is alfalfa. And he did it in the daytime and the nighttime. And the important part of that is that in the nighttime, the photosynthesis isn't happening. So everything that we're seeing in nighttime is just what's coming from the soil and being respired out of the plants. So there's no photosynthesis happening. So here's the key part of this. The difference between the daytime and the nighttime is what we call total net ecosystem exchange of carbon. And so a positive value here of NEE indicates that the ecosystem overall, the plants, the soils, everything taken together, is accumulating carbon. And a negative value indicates that the system is a source of carbon to the atmosphere, okay? So what we see here plotted over time then, and this is just his daily stuff, and you can see it bounces back and forth, and then he averages it and aggregates it up. And so these dashed lines here are the net NEE, or the total NEE over the season. And the takeaway from this is that in this grass and alfalfa system, there's really this very short time period during the growing season when the system is a carbon sink. When carbon is being taken out of the atmosphere and into the ecosystem. The rest of the season, wintertime and late in the summer months into the fall, the rest of the season, the rest of the year, the system is a carbon source to the atmosphere. Even though it's a very productive alfalfa or very productive grass, these are cool season grasslands, stay in it. So during the winter time, the system is a net source of carbon. Net source of carbon. There's this brief period of green up when it becomes a sink, but then as photosynthesis slows due to nutrient water limitation, it becomes a source to the atmosphere again. So it's a precarious time period, even in these very productive systems, that we could be accumulating carbon at all.
In that late season part of the year, if you're below surface activity is basically
Outstripping MPP.
letting it go.
Right, the microbes are winning.
Yeah.
And of course, if you did the same graph for corn, you would see a different shift. You would see a shift in there'd be more positive in EE during this part of the year with the warm season grass,
Yep.
but less during the spring and less on the shoulders of the season. Yeah. I just like this. I could stare at this forever. Especially the daily stuff. I mean, here he's doing it like daily, and then these are harvest times for the alfalfa and the cool season grass. And you can see with each harvest time, the system just plummets and becomes a net carbon source. I always get it back. Net carbon source. So they harvest, and all of a sudden the microbes are winning. And then it builds up, and it becomes a sink again. So I want to talk more about the Wicks experiment that I introduced during the plenary session today. It's these big plots, it's field scale equipment. These are the treatments that we've been looking at. I described these earlier. One of the things I didn't say earlier is that it's important to note that each one of these systems has 4 replicates, and each phase of each system is in place every year, which greatly expands the number of total plots that we have to deal with. So for the corn soybean system, every year there's 4 corn and 4 soybean plots. And for the corn, oats, alfalfa, every year there's a corn, year 1 alfalfa and year 2 alfalfa. So it's a lot of plots, 78 plots altogether. So I talked a little bit about Greg's work. This was his PhD work. This was a paper he published in 2012. The title is Soil Carbon Lost from Mollisols of the North Central U.S. with 20 years of agricultural best management practices. So I mentioned this, sort of showed you the big aggregate picture earlier today. This breaks each system down into 4 different soil depths so that we can see where carbon is being lost from. And I'm guessing you can't read this, but this value here is the change in soil carbon in grams of carbon per kilogram of soil. And here we're indicating whether that change was statistically significant or not. And basically, if there are letters, it wasn't. So here in this continuous corn system, at 0 to 15, 15 to 30, 30 to 60, we were losing significant amounts of carbon. There was no change at 60 to 90, and then down here is the aggregate change, and that was a significant loss. Similar thing for the corn soybean system, although not as deep. We weren't losing at the 30 to 60 centimeter horizon. Similar for the corn, corn soybean with a cover crop. And then we get into our forage systems, and you can see that interestingly, in the surface horizons where we have alfalfa, we're not losing carbon, we're not gaining it either, these are not significant. But in that second layer, the 15 to 30 centimeters, we are losing carbon. And then we're not at depth. And then here's the pasture, the cool season pasture, where we're actually gaining carbon. It's the only positive number on here. It's statistically significant, but it's only in the 15 centimeters of the surface. Below that, they were all negative values, but they weren't statistically significant. So even below 15 centimeters in the pastures, we're losing soil carbon. Anybody want to talk about that?
On that forage system, second one up from the bottom,
Yeah,
is that because at that depth in that type of plant system, you have the most activity going on at that depth for microbial?
that's a hypothesis. We don't have the data to bear that out yet, although that's something that we're keen to explore.
Is he looking at maybe doing like instead of a corn on corn or corn bean, do like corn after a carbon crop or a rye, and then beans after a rye, and see if that would maybe be like a offset, maybe get it back even more of a neutral or even a positive, or
So the answer is we are going to try some new things. But first I want to say that one of the tricky things with these long-term experiments is maintaining the integrity of the long-termness of it and not changing it a lot along the way. But we do have some nested experiments going now. And they're not exactly what you were proposing, but it is that sort of throwing the kitchen sink at it thing.
Yeah.
Where we're trying to actually,
Are you trying to do a little bit of that with like an extended rotation? Kind of, maybe with the oats and the alfalfa.
Yeah. No, I like the thought. We haven't thought of doing an extended rotation per se. It's been more about doing more cover crops, like trying to get on even more shoulders and more seasons cover crops, but also adding more manure and also reducing tillage even more. Because right now we do some strip till and some minimum till, but just having no till at all. That's one of our
I guess,
directions we're
I don't
heading.
know.
But I like what you're thinking
The
about.
way I
extended.
was going with that thinking is I'd like to think that on my farms where I grow corn and beans each year in a alternation or rotation, I still do interseed a cover crop, either whether it's legume or grass. But like as soon as the beans are harvested, I plant a rye, or I plant a rye or a oat or a clover in the growing crop. So when one is done, there's another one going. Maybe that's trying to offset, maybe keep it, I don't know. The big buzzword is cover crops. I kind of like to think maybe that it's partly a carbon crop also.
I like that concept.
I call, a lot of people call it cover crop, cover crop, cover crop. I like to call it a carbon crop, maybe just because
You're talking about grassland.
Capturing the sun.
yeah, that's the big thing. Put the sunlight in the sun.
An MPP crop. One of the other things that we're looking at now, given some data that we have, is that maybe these alfalfa plots are actually exuding some enzymes into the soil at that depth that are stimulating microbial activity, and we have a little bit of data pointing to that. So, but before we leave this, I just want to say, I often wave my arms about how the cool season grasslands are the only system that we're accumulating carbon, but that they're only accumulating carbon in the 15 centimeters.
So
They're
what's
still
going on at
losing
depth?
what's going on at depth. Well,
What's your thought about
most roots in the cool season grassland are in the upper 15 to 30 centimeters, I usually say. So we don't have much root input below, say, 30 centimeters. That's part of it.
But you said it's a loss, right? Not that it's staying the same. Did you say at depth it's actually?
Well,
it's
they're negative values, but they're not significant. So you're right, they're staying the same, but it seems to be pointing towards a loss. One question we have is like, are we in a situation here where we're burning off old prairie carbon because there just isn't any root input underneath those? And the next paper is going to actually also look at the prairie systems that we have and try and get at that a little bit.
I've got a question for you.
Yes.
When you're talking about the grass and pasturing. When I was at University Farms 4 or 5 years ago, you're actually grazing too short. And that will not affect that. If you graze a little higher, 6 to 8 inches, I think that would negate some of that, not all of it, but some of it would help.
Oh, grazing, when you said too short, I thought you were talking about too short in the season, but
Their height, they're grazing
Yeah.
down to 3 to 4 inches, or even less in some cases. I graze, I'm at 8 inches, 6 to 8 all the time. Or I try to, unless they're kicking it,
our target is 6 inches. I don't know if you were at our plots.
but right around, to just north of the barns, that time I was there.
Yeah.
Well, that might be longer than 4 or 5 years ago, maybe 6 to 8 or
Yeah. How much residual to leave behind is an ongoing argument.
that determines how much root mass you're gonna have,
Yeah.
and how fast it's gonna regrow.
Yeah. Okay, so then what Anna did for her PhD was look at these same plots and look at the particulate organic matter, which is, as I mentioned earlier, that stuff that if you picked it up in your hands, you would still recognize it as plant material. Because it's a pool of carbon that we think should be sensitive to changes in management. That big passive soil carbon, we generally aren't going to see changes in that over the lifespan of a graduate student, let's say 2 or 3 years. Greg had to look at archive soils to get this 20-year difference. And so she just focused on the particulate organic matter and found that in the pasture and also in the alfalfa system, again in the surface horizons, this time to 25 centimeters, that we are piling on a pretty fair amount of organic matter, of particulate organic matter compared to the other systems. And that input, while that's not sequestered carbon, it is the input that ultimately leads to sequestered carbon. So that was interesting to see that we are getting more in those systems. Matt Ruark published this study looking at fertilizer application in some different plots. This is not from the Wicks plots. And this is pretty busy, but the takeaway message from it was that here we have a low nitrogen, a recommended nitrogen, and a high nitrogen treatment in corn. And here's all the carbon inputs. So this is the MPP that I've been talking about from those systems. And then this is how much carbon is removed from those systems via harvest. And the net should be the carbon that's left behind that theoretically could accumulate in the system. And so the takeaway point here is that there's a lot of carbon piling up in the system as a result of the management. And yet when they looked at soil carbon change over about a 30-year period, they saw no significant difference in the high nitrogen or the recommended nitrogen and a loss in carbon in the low nitrogen treatment. So even with piling up carbon year after year after year, they're not seeing an increase in soil carbon. And in some cases, they're seeing a decrease in soil carbon. This is a distillation of Greg's work, but including the prairie and the CRP, which is a warm season mix. It gets a little convoluted because these were 10 years old and these are 20 years old. But the takeaway point here is, again, that the grain and forage systems were losing carbon. The pasture was holding on to what it had. It wasn't significantly different from zero. But neither were the warm season grasslands, which we would think should be putting roots deeper and leading towards more carbon sequestration. Again, they're only 10 years old. How old do they have to be is an open question before they might start sequestering carbon. We're now 20 years out, so this year will be the year that we take those deep cores down to a meter and once again look at whether or not these have accumulated or not. And in the meantime, we've been doing some interesting experiments with these where some of these get grazed, some of them get harvested as bioenergy crops, some of them just get burned like a prairie enthusiast would manage it, and some of them get nothing at all, it just piles up. So should be some interesting stuff. Now, Erin Silva and her grad student Leah have recently done some microbial work with the soils in these Wicks plots. And what you'll see here is that the amount of microbial biomass, so this is bacterial and fungal biomass, is higher in the pasture systems. Starts to go down as we move into the more and more annual and more disturbed systems. So there's just less microbial abundance. And again, it gets back to this tension of how much activity of the microbes do we want and how much total microbial biomass do we want? We want more biomass because that should lead to more accumulation of carbon. We want to slow down the activity, or at least direct the activity at certain times of the year. And how we direct that is sort of an open question and what we should actually be trying to do. And so, just to get a little bit academic here again, when we think about once the carbon gets to the soil, what happens to it? That's what I'm trying to depict here. So I've been mentioning these inputs of carbon as biomass. Eventually that turns into what we think of, what we classify as particulate organic matter. That's that plant material that's just sort of accumulating, and it could be turned off into the atmosphere as CO2, or it could end up as microbial necromass, which is the bacterial and fungal dead bodies that eventually get turned into what we call mineral-associated organic matter, or MAOM. And so this minerally associated organic matter is really that carbon pool that we consider sort of sequestered, because it's organic matter, it's carbon that's bound up with clay particles and silt particles, tied up in aggregates. It's the stuff that we think is stabilized. And what we're learning more and more lately is that virtually all of that has been processed by microbes. This stuff that's just piling up is not just turning into this. I guess it's maybe a no-duh, but now we have the data to show that the microbes are the ones who are doing that. And their enzymes are a key part of that. They produce enzymes that help break down the biomass, the plant biomass. They themselves die, and then their neighbors eat them and turn them into biomass. So that it gets processed by microbes for many, many, many generations, and eventually turns into this minerally associated organic matter. And as I mentioned, there are these big drivers on how this is happening, but within the system, we think of these three variables as being particularly important for this process. The carbon to nitrogen ratio of the plant material that is coming into the system, because that affects which microbes can deal with it. So if you have a bunch of woody biomass that has a high carbon to nitrogen ratio, then fungi are going to go to town on that, because fungi have this ability to exude these extracellular enzymes that help break down that material. But what fungi also can do, because they're multicellular, is break down the wood right here, drawing on nitrogen that's over there, because their bodies are multicellular. So they grow hyphae and mycelia through the soil system that helps them to break this down by pulling from resources elsewhere. Whereas bacteria are just little single-celled bodies, and they have to get all the resources they need from wherever they're doing business. And so they struggle to break down stuff with a higher carbon to nitrogen ratio. As a result, we've always been really happy when we look at the microbial biomass in the soil and see more fungi in the soil, especially in agricultural settings. Because the more fungi that are in the soil, we think indicates that we're putting lower quality plant material into the soil that has a better chance of eventually ending up here. Now that paradigm has been up for debate, and is still up for debate in the literature.
What is the balance between bacteria and the fungi?
What is the balance?
Yeah, 1-to-1, 2-to-1?
In terms of their total biomass? I don't know the answer to that question.
Is it measured?
It is measured, yeah.
It's measured.
Yeah. Do you know off the top of your head?
No, I mean, it's known. I don't know it off the top of my head though.
I want to say that the fungi never dominate. I mean, there's systems that have more fungi, but the bacteria still dominate in terms of total biomass. Unless you're, right there where piece of wood is decaying in the forest. That's a good question. I don't know the answer off the top of my head.
That's one reason why, like the fellow in the front there, we use interseeding or prolagating with your grasses to help maintain that.
Yeah. So where I was going, and I think what you're saying is related to it, is that historically we've thought more fungi must be a good thing. Plant material that has a higher carbon to nitrogen ratio must be a good thing. It's harder to decompose and therefore likely to stay there longer. And now what we're finding is lots of data sets that sort of flip that upside down and show that actually systems that have a juicier material, lower seed to N ratio, like a legume, whether that's clover or alfalfa, that material tends to end up here more readily. And we're not really sure why, except that we think that it has something to do with the physiology of the microbes that are doing the processing. And right now we kind of just call that physiology carbon use efficiency. It's how well do I, as a microbe, break down a unit of carbon for each unit of, how well do I build my own microbial carbon for each unit of carbon that I have access to? And so if I can be more efficient, then more of that carbon ends up here and less of it into the atmosphere.
Is there any chance that you know of some bacteria that are better at this than other bacteria? Leading to a question of, couldn't we be inoculating our soil for better carbon sequestration?
Yeah, I haven't seen, in the bacterial realm, I haven't seen folks talking about that much, but it could just be because I focus more on fungi. There are certain types of fungi that actually help the plants get nitrogen, arbuscular mycorrhizal fungi and that sort of thing. And so there's a lot of talk about trying to inoculate soils with, well, I think it's more than talk. People are selling arbuscular mycorrhizal fungi now to inoculate soils. Whether or not it actually improves things, I would say, is still an open question.
We're gonna talk a little bit tomorrow about inoculation,
Good.
especially with rhizobia, because it depends a lot on the conditions in the soil, and you could put something in and it might not be viable first, second, it might be great and alive, but you put it in the soil, there's so many competitors in there that it doesn't last a day. That's something I would argue we're still learning a lot about what that competition looks like in the soil. We just don't have enough data yet to say you can put something in and have it stick around. It's really an unknown.
You have to
Kind of
compete
theory.
or coexist.
What's that?
Compete and or coexist.
Yeah.
It's not the kind of thing you can just decide one day you're gonna top dress this product and have it be a magic boo-boo juice. You gotta kind of.
Apparently people do decide that.
Yeah, the salesmen have that stuff, but you kind of gotta get a whole system, you gotta get the ball rolling, this snowball building up.
Now, one of the generalizations that I've come up with in the microbial realm, not that I came up with, but that emerged for me, was from a study we did where we just did a bunch of microbial samples across North America. And there were some from ag soils, some from forests, some from wetlands, et cetera. And one of the main things that jumped out immediately was that all the ag soils had rhizobia. So I don't know if that's because of the salespeople have been so effective at selling it, or they're just there because of all the legumes.
Yeah.
Okay, so we're trying to get it here. Yi Chao Rui is a postdoc who has been working on this a little bit, and he has some data from our Wicks experiment that are starting to point to some interesting things. So here we just have our continuous corn and our pasture, our cool season pasture, and this is that organic corn, 2 years of alfalfa rotation. And so again, we're piling up more particulate organic matter in these perennial systems, no difference between pasture and alfalfa. The microbial necromass, the amount of dead microbial bodies, again is building up in those two systems. But only in the pasture are we seeing increases in MAO, where the carbon that we want to see accumulating. And so we really don't know why, this system's, why the organic corn alfalfa system, has the early indications of carbon accumulation, but then eventually are not turning into mineral-associated organic matter at the rate that the pastures are. And part of it we think might be this thing I was saying earlier. I don't think I included the slide, so I won't switch. That we're seeing much higher enzyme activity in the legume system, as whether that's related to the rhizobial activity or whether that's related to some other enzyme exudation pattern. We don't know at this time. But
The pasture system does this, and I'm going to a physical thing here, because nutrient management says everybody else who's not pasturing has to physically incorporate, especially if they're CAFO, do soil destruction, and we're mass loading all this organic matter, whatever, but we're destroying aggregate in the process because it's required. The pasture people, have you measured dissolvable P leaving the pasture system? It's never incorporated. And is there a potential interaction as that cow pie delivery system being so healthy?
I'm not exactly sure what you're asking me.
Well, I mean, I think it's just one thing going on here.
I guarantee you that. Yeah. So we have looked at phosphorus leaving pasture systems, and it's quite low. That was part of your question.
That's part of it, okay. So it's not escaping that realm of things.
We've looked at dissolved phosphorus. We've looked at phosphorus adsorbed to particles. Both of them quite low.
What kind of loading is going on in the pasture? Anything near the nutrient management numbers that people are putting on when they're putting on 8,000 gallons or 10,000 gallons of a liquid manure?
No. I mean, the only loading that's happening is occasionally we fertilize with nitrogen, to the tune of 50 pounds every couple of years just to replace.
Loading going on because it's pasture.
Yeah.
That means four-hoof drive deposition of manure.
Right, but they're recycling what they've grazed in those pastures.
Correct.
So whether that's loading or not is a question. But yeah, I'm with it. It's much less loading than what you'd be getting where you
I think
spread
we need to
them.
load them up.
Load up the pastures?
Just measure it rightly.
Okay. Rather than going out and sprinkling rhizobia and AMF on the soils, I would just rather go out and sprinkle pastures around the landscape. And they seem to be doing what we want them to do.
Yeah.
Including, if you were here for my noon talk, be pretty profitable. So, all right. So I'm with you on that. That's interesting. This is all just more data to sort of undergird that argument I was just making a minute ago. The fungal to bacterial ratio of the necromass seems to be the same in the alfalfa system as it is in the pasture system, but there's something still different going on with respect to the carbon use efficiency. The efficiency that that the microbes make their bodies seems to be higher in the pasture. And so whether this is because those microbes are fundamentally different microbes or their physiology is totally changed is an open question.
So you mentioned that, I'm thinking about this finding you had where the organic systems are basically blowing off more carbon than they, than over time, and they're not making it to the stabilized stuff. So do you know what enzymes were found to be higher in some of the organic systems that include legumes? Because often, you can tell what processes were higher in that system relative to other systems looking at the
We do know,
enzymes.
I'm drawing a blank right now. There
That's
were two
okay.
enzymes in particular that jumped
I
out
was
at
just
us.
curious, because often that'll tell you what that process is that's higher. That's really interesting. I
Yeah.
find that really fascinating.
And one other thing is, in the 3-year system, you have 6 months between corn and oat establishment of nothing growing, right? But in the pasture, you're 100% covered. In the corn system, there's, over 2 years.
No, the oats are established with the alfalfa at the same time.
No, but after corn harvest to oat planting the next spring, there's months there of
Yeah.
nothing growing, right?
Yep.
So there's less coverage in the corn on corn,
Yep.
right? It's half the time covered. In that, there's 4 to 5 months, maybe 6 months of no coverage. With the pasture, it's continuous coverage, right? With fungi, so they need a continuous source of carbohydrates.
Yeah.
All the system does, right? So.
And the fungi seem to be okay. I mean, it's not that there is disturbance too from the planting of the corn and whatnot. And we're not, we tend to think that the disturbance breaks up the fungal bodies and their numbers should go down, but they're not.
But from that step to that step, maybe that's
Yeah.
that's like the one difference from the pasture, is 6 months of nothing growing
And the disturbance.
and disturbance.
And some nutrient loading. It's a lot of.
Yeah.
So we're trying to sort that out with what we call structural equation models. These are hot off the presses. I don't even know how to interpret them, except that I thought it was really cool that the continuous corn and the pasture had fundamentally different patterns. And the way you read these basically is that the black lines are all hypothesized relationships between everything we can think of. So this is what we call a kitchen sink analysis. Throw all the variables in there and see what's correlated. The black lines are hypothesized. The red are significant relationships based on the data that are negative. So in other words, a higher C to N ratio of the palm results in lower aliphatic carbon, and higher aliphatic carbon results in more mayom accumulation. On the other hand, in the grazed pasture, the carbon use efficiency of the microbes seems to be positively and directly related to mayom storage and bypassing some of these other things that we think are important. So I guess I'm just showing you this to say we're really intrigued that there might be some really different mechanisms going on here related to where Sarah's trying to go, and we're going to keep digging into this. So. I feel like I've been talking way too long today.
What happens
Go
if
ahead.
you would emulate grazed pasture except for mechanical? You do all the benefits that, you probably have 3 or 4 grasses in there,
Yeah,
maybe more.
yeah, some clover.
Probably some clover. And we just raised a diverse forage.
And we just raise it.
We raise it and we harvest that.
Oh, yeah,
Mechanical harvest.
yeah. Would we still get the same benefits?
Yeah.
Is a question. Yeah,
You kind of do the same thing, but on the other side, have your pasture that is just automatic, keeps happening. But
perennial.
when you have your corn, oat, alfalfa, change that to a no-till system instead of an organic till system, which
Yeah.
is hard without chemicals.
Or maybe this idea that's, I think, kind of a European idea of a lay, where you have pasture in rotation for maybe 4 or 5 years.
Yeah.
And maybe you get whatever benefits you're getting here in the microbial community from building that up for a few years, and then you go back into a grain. These are all things that I think are open. I mean, as a grassland ecologist, I keep asking, why do we want these grains so badly? But I know we're at the small grains conference, so. Go ahead, Julie.
Oh, just a quick question about alfalfa and how, as a semi-perennial, multi-year crop, how similar do you think the benefits might be in systems that are including multiple years of alfalfa to a grassland?
Yeah, well, they're not really bearing out to be as similar. They're not holding on to carbon the way that we want them to.
You know,
Do I know why?
Export.
Polyphenol oxidase is one of the enzymes that
Oh,
just
did you
came in my
remember?
head. It might have something to do with the enzymes that they're letting go into the soil. It's a good question. They still get disturbed, as we were talking about, every 3 or 4 years. Maybe it's just that disturbance is enough.
You're also exporting your crop off, unless you're putting the herb back on.
You're pulling off a lot more of the crop. And I also wanted to say the root architecture, I think, is critical for inputs of carbon. And so even though the cool season grasslands are pretty shallow rooted, they're a very dense fibrous root mass that's turning over constantly. Alfalfa puts down a very deep, thick root, and it has lots of roots, but they don't turn over and they aren't quite as dense and fibrous as a grassland system, so that could be a big part of it as well.
Yeah, you mentioned a diverse forage. So your measurements that I'm guessing it was a pure alfalfa stand. And I'm thinking here, gosh, the old timers, they were, they wanted that right mix of alfalfa and orchard grass and timothy, and I wonder what it would be like if you had a 50% alfalfa, 50%
Yeah.
grass. It just we give up so much when we try to have progress, and you want that pure alfalfa. And just
Specialization.
We have a scientific background like we do, but this year's winter kill, fairly severe. And I have 2 expansion areas in the middle of a more traditional family area. As customers, all 3 of them. The winter kill on the pure alfalfa guys, mostly brought on because they wanted high vegetable lignin. And our university does suggest economically, I'm I've argued with Dr. Sundersander about this terribly so. It's very inefficient. But the small farmer in the middle, small being 180 cows, has, population-wise, I would say 60-40, and his alfalfa winter kill was nil because of the survival of that grass, the diversity, and he's a little bit different measuring guy. He does some things differently. But the day after the second 45 below night, before the snowstorm, he's out there taking soil temperatures above his tile lines. Because we have a test plot there. And his straight alfalfa at 12 inches was 4 degrees colder than the alfalfa grass mix over those tile lines. 4 degrees. That's a lot.
Your biology activity going on.
So her point about the core and quiet time after harvest, that nothing's alive out there.
Yeah,
Just degrading root systems
Yeah.
of a massive corn plant, but nothing's alive. So the winter kill of the two big dairies, of all their, I mean, they're scrambled for forage in their feed all summer long and all fall now. It's all set up again to do it again. They're gonna harvest what hay they do have late, and they're not gonna leave that growing like they should. We need to get back to alfalfa grass mixes. I've said it for a long time. I wish I had less hair, and I'm probably older. But, you know, the wisdom of our grandfathers is pretty large, accidentally as it may have been. Diverse grass, alfalfa, legume, and maybe not just one legume. I mean, who makes dry hay anymore than the exodus of red clover, which was a big mistake, only done because we couldn't get the stuff dry. Well, we're dry bales today, not very much. So diverse legumes and diverse grasses.
yep,
That needs to go into your system.
yep, I like that idea a lot. We've been talking about doing this grass lay system, and I think this sets it up perfectly for that. I like that. It'll take 10 years for us to see some results, but that's okay. We're into long-term
We're looking at
experiments.
it.
This is really good stuff.
Do you think saliva from the animals grazing has something to do with it? The enzymes they exit out? I think it's got something to do with
I
it.
won't dismiss it. A simpler explanation might be exudation from the roots when the grasses actually get grazed. We know that when grasses get defoliated, that they exude carbon into the soil as an evolutionary adaptation to stimulate microbial activity. And so again, getting back to this tension between, like, do we want a lot of microbial activity or do we want to slow it down? We want a lot of microbial activity while the plants are growing. And so it could be that the grazing, just the mechanical, physical grazing itself is stimulating things in the right direction. The saliva on the grass and that eventually getting in, that's a little bit more indirect for me, but I wouldn't dismiss it.
So, are you seeing more of that speaking of kind of diverse systems, do you see greater carbon storage benefit from a system that has both warm and cool season grasses? Because a lot of the best carbon capture, for lack of better language, is happening during that most active growth stage. So if you have greater diversity of species of both like grasses and forbs, you have more active growth stages, so you're seeing more?
That's a great hypothesis. I'm smirking because my first experiment I tried when I got here from California was complementarity is this term we use in ecology. You know, that complementary resource use should maximize everything. And so we tried to get warm season and cool season grasses commingling.
I don't know how that works.
We couldn't get them to commingle. One always wants to dominate.
Okay, got it.
And especially under grazing management, it got really tricky. I love the concept and I love where you're going with it. I think what we tend to do more of now, and I talked to Gene Schriefer, who's here, he's doing this now where he has C3 pastures and C4 pastures, you know, and he moves his livestock around and tries to graze them when they're productive and when the other one's not productive. Trying to get them to grow together. It happens in Kansas and Nebraska naturally, but it's really hard to get it to happen here because our weather is so extreme, it seems. Like in the cool season years, the cool season grasses just kicked all the warm season grasses out. And could never really get the warm season grasses to dominate.
There's some work on crossbreeding that does roll in is useful. Up northern, warm season
Yeah.
partial to accommodate what you're saying. I want more of those, more of those. A little more warm season than you would.
So, this has been a fantastic discussion. I'm loath to keep going through slides. I don't want to go through any more slides. I feel like I've browbeat you with data already. This has been fantastic. I feel like I have some good stuff to take home and talk to Greg about doing our experiment next year. Lots of good potential interpretation. I need to send some data to Julie and have her.
Yeah, you see you writing it down.
Any other questions or comments? Yeah.
I did have another question about just kind of the time frame from the conversion of like plant residue or biomass down to that more stable carbon.
Yeah.
What is the kind of scaled time that's maybe optimally happening on? Do you know? Or does it just depend on the situation and whether it's being successfully converted at all?
How long it takes to
Yeah.
get into that pool? I'm not gonna hazard a guess. I'll just say that that pool of minerally associated organic matter, I mean, we are picking up new minerally associated organic carbon in a matter of 2 to 3 years. So some happens.
Something happens.
But that pool itself, on average, in these mollisols in the middle of Wisconsin, on average, they're about 3,000 years old. And some of the other data that I have that I don't want to get into now shows that when we plant into these soils, we liberate a lot of that old carbon. Yeah. So I don't think I'm answering your question directly. It happens, but slowly.
Yeah.
Yeah. We don't move the needle on soil carbon sequestration very quickly. So be skeptical anytime somebody says otherwise. Well, we can liberate it pretty quickly. It's
Right.
hysteresis is the term we use for that. The process happens really slowly one way and really fast the other.
Right, which kind of actually my third question kind of gets to that. Those 7 practices you put up at first that are often proposed as strategies, but might not be borne out in the research. Do some of those strategies still seem to show benefits as far as reducing just kind of the general associated greenhouse gas emissions? You know, obviously they have other benefits in
Yeah.
soil organic. There's a whole host of
Good
benefits
question.
to soil, but I'm curious how, you might not be storing as much soil carbon, but if you're reducing just,
Yes.
general greenhouse gases from better manure management, you're not applying certain types of fertilizer.
The bottom line on that is that the perennial grasslands do better with respect to nitrous oxide emissions. They do emit significant nitrous oxide, especially when they're grazed, because that mineralization of nitrogen leaves a lot of nitrate that gets turned into N2O pretty quickly. But it's nowhere near the amount that comes off when we add inorganic nitrogen to corn or other annual cropping systems. That far outstrips what we see from cow pats and urine patches and perennial grasslands. But the amount of nitrous oxide coming off of perennial grasslands is also significant. We can't get something for nothing. It's almost insignificant coming off of prairie. And I would say the same statement with respect to leaching of nitrogen below the rooting zone. We get very little leaching from below prairie. One of the rubs with cool season grassland grazing, because of the shallow root system, is that if we hammer it, and your comment about grazing it too tight makes me nervous, that nitrate, once it gets below the rooting zone, is gone, and it finds its way to waterways. And so that is something is an active line of research that we have to figure out how to deal with. Maybe it's having more warm season grasses in the system that are deeper rooted and holding on to that nitrate. Yeah. Good question.
Great, well, let's thank.
I'm rung out.
That's great.
Thank you.